Hey, good afternoon, everybody. Welcome to Wi-Fi Troubleshooting Tools and Techniques. The conference Wi-Fi is terrible. I'm glad you would join me after lunch. Hope I can keep you awake at least a little bit. My name is Chris Dawe. I'm at CT Dawe in Slack and on Twitter and in a variety of other places. I'm a small business consultant out of Seattle, Washington. I handle a lot of Mac, iOS, and network planning, deployment and troubleshooting for small businesses, and K-12 education. I also provide project management, project planning services around Apple and IT. I also have thoughts about food, whiskey, and politics that I'd be happy to share with you if you come to Legends and you really want to know. So why are we here today? How many of y'all have users whom you've tried to convince that connecting the MacBook Pro to the Ethernet cable will give them a faster and more reliable connection? Show of hands. Okay, keep your hands up if you succeeded. All right, so in one sense here, we're because the rise of iOS and OS X mobility has transformed our Wi-Fi networks from kind of a nice-to-have add-on to a necessary and critical component of our networks. We now have hundreds or thousands of devices, most of which aren't connecting to the Ethernet network, and a large majority of which no longer even can. So we're kind of forced in this direction. That's one reason why we're here. Another reason why we're here is Tom Bridge's fault. You guys may see Tom Bridge around today. He's made a quick trip to and from. He's a friend and colleague out of Washington, D.C. who helped with the development of a lot of this material. He and I have gotten to know one another over the last 5 or 6 years. And 2 years ago, at this conference, the Penn State Mac Admins in 2014, I suggested to Tom that I was thinking about submitting a session on the fundamental characteristics of Wi-Fi. Now, Tom being Tom, he called my bluff. 6 months later, he dragged me, kicking and screaming, into submitting the proposal for what became 2015's Fundamentals of Wi-Fi full-day workshop. We've since distilled a lot of what we learned in that into a couple of other presentations. We gave one presentation at the London Mac Admins Conference, Macaduck, and remounted the workshop at the Cascadia IT Conference in Seattle. In order to do that, we compressed a full day's worth of material into 4 hours worth of presentation time and renamed the presentation in the workshop Chris and Tom's Wi-Fi Death March. A lot of what is in this material comes from that iterative development process. So, for Mac Admins 2016, I've adopted our workshop sections on troubleshooting and network design into individual but related talks, focusing on converting the troubleshooting section into a standalone piece, and I'm backing away from a lot of the nitty-gritty vocabulary, the jargon, the very inside baseball kind of vocabulary that Wi-Fi engineers use, because to some extent it creates more complexity than you may need if you're getting your feet wet, just getting started with Wi-Fi. So my goal is to introduce some of the fundamental concepts of Wi-Fi, help non-network admins recognize some of the warning signs of bad Wi-Fi, and I hope to provide you with a toolkit to assess your Wi-Fi and help you understand what might be going wrong. At the very least, I hope to give you an idea of what's happening when 60 Macs and 30 iOS devices associate to a single access point and everybody starts slacking Giphy at once. So, our agenda is that we're going to outline some key characteristics of Wi-Fi. We're going to talk about how those key characteristics lead to problems and what those problems look like. We're going to talk about several things that aren't actually Wi-Fi problems but do present as Wi-Fi problems, and they're the kinds of things that make your users complain. Hey, the Wi-Fi is terrible. A toolkit, and then finally we're going to talk about a toolkit that can help you see and understand what's going on. If we have some time, I will tempt the gods and perform some live demos of some of these tools. So starting with some characteristics of Wi-Fi that really are the characteristics that lead to trouble. First of all, it's sensitive to physics. It uses what's called a shared medium, and it uses what's called an unbound medium, and we'll go through these one by one. These aren't all the characteristics of Wi-Fi, but these are 3 that really key in on why Wi-Fi begins to fail. So, saying that it's subject to the laws of physics is a little bit, yeah, well, so what? Everything's subject to the laws of physics. Ethernet is subject to the laws of physics. Now, what's really true is that Wi-Fi is more sensitive to a lot of phenomenon that are associated with its physical properties. You know, to really mess with an Ethernet signal, you need to go mess with the cable. But I can mess with a Wi-Fi signal from several hundred feet away. So power is a key component of how Wi-Fi works. Radio transmitters convert electricity to radio signals. We usually rate or understand Wi-Fi transmission power in milliwatts or decibel milliwatts. For the purposes of today, I'm going to stick with decibel milliwatts for a couple of reasons. One is it's what a lot of vendors use. And two, the math is really hard, and my degree's in American history. So we're going to stick with one element of representation. If you're going to dive deeper, you'll have to get to know the translation back and forth and what the meanings are. But for today, we'll stick with dBm. Power is a key element in producing a Wi-Fi signal. Different devices, both clients and Wi-Fi access points, transmit at different levels of power, and the power rating affects the effective range of transmission of your Wi-Fi. Once we've got the signal out over the wire, we start to deal with physics a little bit more. We start to deal with the inverse square law, which is another key element of how we think about signals. The inverse square law states that the intensity of a signal radiating from a point source is inversely proportional to the square of the distance from that source. You know, what does that mean? It means the further you get away from some kind of radiation emitter, the weaker the signal is and the lower the intensity is. So if you stand, 5 million kilometers from the sun's energy is one thing to you. If you stand on Mars, very much another. Attenuation is what we call the loss of signal intensity. Attenuation happens in the Wi-Fi environment for a couple of primary reasons. One is that it just naturally happens over distance. The signal travels through the air and loses strength. The other is that Wi-Fi has to travel through materials because it's usually used indoors, and even if it's used outdoors, it often has to travel through things like trees or rain. So different materials attenuate the Wi-Fi signal differently, and paying attention to that will help you understand what's going on in a Wi-Fi environment. This brings us to what we call the rules of 3 and 10. And this is a little bit of a, there's a lot of text on this slide. Really what this describes is how we can look at things like the RSSI number reported in your Apple Wi-Fi menu item. When you hold down Option, click the Wi-Fi menu item, you'll see RSSI reported, and the numbers increase and decrease as the signal increases and decreases. And a decrease in RSSI, received signal strength indicator, of 3 dBm represents a halving of signal intensity. An increase of 3 dBm represents a doubling of signal intensity. If you decrease the signal 10 dBm, you reduce it by an order of magnitude. That is, a tenth of the signal. And if you increase it, you multiply the intensity by 10. So, who's ready for math? Ready for math? So, on the screen, I have 2 RSSI readings, -66 and -50. Anybody want to take a shot at how much weaker -66 is than -50? What's that?
40.
A 40th?
Yeah.
What t-shirt size you wear? Winner. I got one for you after the show here. So that's right. -66 dBm is 1/40th of the signal strength, 2.5% of the signal strength. And one of the things that this tells us is that Wi-Fi is, as much as we complain about it, if we can, both -66 and -50 are usable signal levels. And if we can lose 97.5% of our signal strength and still work with the Wi-Fi network, we're talking about a technology that's got some fault tolerance and robustness built into it. So comparative measurements of our SSI and the corresponding weaker and stronger signal levels imply attenuation. But if I were to try to survey signal strength by walking around, option clicking the Wi-Fi item in the menu bar, and then writing down my results on a piece of paper, well, I don't want to do that, and neither do you. So there's some other tools to visualize this. We've got some tools that do this for us. A heat mapper application allows you to import a floor plan, scale it using a tape measure or laser rangefinder, what have you, apply that distance to the floor plan so it knows how far apart things are, and then you take the computer running the heat map application, walk around and collect samples. When you're done, you tell it I'm done sampling, and it builds a map for you. It shows you where signal is strong, where signal is weak. In this case, we're viewing a screenshot from NetSpot Pro, which is the only Macintosh compatible, or I should say Macintosh native heat mapper. And in this case, the representation is warmer colors equal better signal, cooler colors equal worse signal. NetSpot Pro. So the second key characteristic of Wi-Fi is its use of a shared medium. And that's going to be a bit of an esoteric concept. We have to start with the idea of frequencies and channels. So frequencies are measured in hertz, which represents times per second. And it's essentially just a measurement of how often and how rapidly does the wave go up and down. In the world of Wi-Fi, channel is the term that we use, and it's effectively shorthand for a particular frequency. The FCC assigns Wi-Fi, in the United States at least, a series of frequencies that it's able to use, and that gets turned into channels so that it's easy to refer to. I don't have to remember a gigahertz down to the nth degree. I can just remember channel 40. Easy to use. Wi-Fi uses channels in kind of an interesting way. When a client associates to an access point, that means essentially joining the network at that access point, that client transmits and receives on the same channel as that access point. So if my access point is on channel 44, the clients that join it also join channel 44. Every additional client that associates to that access point also transmits on that channel. And here's one of the key pieces when you think about Wi-Fi troubleshooting, Wi-Fi design. Only one device can transmit at a time. It's a shared medium. So let's pretend that you and a friend are talking. Very calm conversation, back, forth, and then you get excited about something, and the conversation ramps up, and suddenly you're talking over one another, and you have to stop and ask one another to repeat what each other said. That's similar to how Wi-Fi behaves. Imagine this phenomenon at a bar with 10 or 12 people. Think about those conversations. Everybody starts, and then everybody stops. And half the people start, and a quarter of the people stop. And eventually the conversation continues. But if multiple devices on a Wi-Fi network attempt to transmit simultaneously, their signals collide, assuming that they're in range of one another. And those signals won't be received. And here's a visual example of that. And this is kind of a complicated example because it uses an older application called Wi-Fi Perf. This is a network bandwidth tester. And the scenario for this network bandwidth test is that I had two computers, one running iPerf server, one running iPerf client, attached to a single AP. That was the entirety of the network. And I started a bandwidth test. Just essentially how much data can I send back and forth between these computers using TCP. In the middle of the test, I added a second pair of computers running the same test with one another on that access point. So now I have 4 computers running on that access point, chewing up the bandwidth, and you can see the moment where that second computer drops in. Suddenly, the effective bandwidth of the first test drops to less than half. So let that sink in for a moment, because every time you add communicating clients to a Wi-Fi network on a single AP, this kind of thing happens with your bandwidth. every additional client represents a spreading out of the available bandwidth over all of those clients. This is not like an Ethernet switch. And so that's a really important thing to be aware of. This takes us to the way that Wi-Fi goes about trying to understand when other things are transmitting and when they're not. On traditional Ethernet, where you plug a cable into a switch, we use something called carrier sense multiple access collision detection. And what that means is that part of what the Ethernet cable is doing and what the Ethernet ports on the switch and your computer are doing is they're detecting as soon as you try to send data if there's data being transmitted. And if there is data being transmitted already, the Ethernet interface says, whoa, stop. We stop the transmission. We do what's called going into back off at that point. We set a random amount of time where we're not transmitting anymore. We try to let the other transmission on the Ethernet finish, and then we try again. Wireless can't listen while it's transmitting, and so this is much more of a problem. Wireless looks for acknowledgments of transmissions and then retransmits if it doesn't receive that. So that is, if I'm transmitting to an access point in order to move data over the network, and I don't get an explicit acknowledgement from that access point, like I go ahead and try again. I assume failure. And that leads us to what's called the hidden node problem. Up until now, we've assumed, oh, and by the way, that is called carrier sense multiple access collision avoidance. We listen, and if we don't hear anything, we talk. But if we don't receive an acknowledgement, we listen again and then we talk again. And that leads us to the hidden node problem. Up until now, we've assumed that everyone can hear everyone else. And that leads us to one of the biggest problems in Wi-Fi. So I said that clients will wait for quiet and then transmit, but in certain scenarios, you end up with a problem. Station 1 is associated to an AP, Station 2 is associated to the AP. Both of them can hear the AP, but neither of them can hear each other. So in the case where both of them try to listen and then transmit, neither of them hear the other one transmitting, and they'll go ahead and try to transmit anyway. Collisions happen, acknowledgements fail, the devices try to retransmit, and then the situation snowballs until it leads to congestion. This is a visualization from Insider Office from Metageek. The increasing amount of traffic generates a larger number of collisions, which in turn generates a larger number of retransmissions, which generates a larger number of collisions, which generates a larger number of retransmissions, and the whole situation just snowballs to the point where no one can transmit effectively. On the screen, you have an example of the network from my local coffee shop in Seattle. Metageek says that the utilization is sustained at approximately 75% of the available transmit time. At that level of utilization, multiple clients associated with this network on channel 10 that we're focused on are likely sending large amounts of data, and they're probably suffering from proximity to other networks. Those in turn cause collisions, force retransmits, and cause the utilization to go up. Now, this is a problem that can be bad in a well-designed network, with lots of clients to send and receive from a single access point. I think these conference rooms are a good example. The problem grows worse when you have a poor network design in which you have multiple access points and their clients on the same channel, and they are able to transmit and receive, and all of the APs can hear one another. I should probably restate that. Problem goes worse when you have multiple access points and their clients on the same channel. that are within transmission receiving range of one another. So in the screenshot behind you, you've got a network called Hamstring that someone has thoughtfully built with 4 access points that are on the same channel, and they're all within range of one another. They can all hear one another. So that means that everything that's associated with any of those access points is contending with the fact that those 4 access points are also competing with one another. And when we talk about design later this afternoon, we talk about how to avoid that. So the third characteristic of Wi-Fi that I wanted to talk about is the unbound medium. What an unbound medium is something that essentially has no physical limit, whether in theory or practice. Ethernet is a bound medium. It's confined to a cable and to switches, and it's very difficult, as I said earlier, to inject disruptive signal into it. Wi-Fi transmissions, on the other hand, radiate through open air, and they therefore conflict with anything else that might be radiating on the same frequency. The other piece of the unbound medium that's important is that whereas Ethernet itself is physically constrained by standards, such as the length of the cable, and constrained by the number of available network ports you have on your switch, Wi-Fi signals can essentially travel unlimited distance, and you can essentially tack an unlimited number of clients onto a Wi-Fi access point. And so when I said that increasing numbers of clients share the same available bandwidth, the more clients you add, the less available bandwidth there is per client, and the more the load goes up. Questions about that before I go on? No? Okay. So let's go on to common Wi-Fi problems. And I'm going to talk about what are essentially 5. I'm going to talk about signal and coverage issues. I'm going to talk about co-channel interference, adjacent channel interference, which is similar but different. I'm going to talk about resulting contention and congestion, and I'm going to talk about radio frequency interference. Signal and coverage are our most basic, and we'll see these screenshots again. Compare the RSSI reported in the Wi-Fi menu item to observe different signal strengths. But really evaluating signal and coverage requires moving from just pure signal levels to understanding signal to noise ratio. There's always background noise in a Wi-Fi environment. If you option click on your Wi-Fi menu item, you'll see a noise listing, the amount of noise, essentially background radiation or background broadcast that your Wi-Fi interface is picking up in addition to the signal. We subtract the level of noise from the level of signal to derive a number that essentially says how much stronger is our signal than our noise. In the case in front of you, you have SNR of 35, which is pretty good. You know, this is a Wi-Fi signal from Adrian Granados, a really excellent application, and you should give him your money. Various applications document and assign signal quality levels to various signal-to-noise ratios. If you look at MetaGeek's documentation, NetSpot's documentation, Adrian Granados' documentation, they all really seem to align. So you can essentially take a signal-to-noise ratio and say, yeah, that's an excellent signal, a good signal, or I'm surprised this works at all. And you can use, again, a heat mapper like NetSpot to map out your signal and signal-to-noise ratio. And again, my office, you know, this is a map of where my office is pretty small, and I don't even really need 2 APs, so I was lazy about my access point installation. You know, that's on top of a box, that's on top of a desk, and then when I did a map of my signal-to-noise ratio, I determined that this meeting area up here in front of the big whiteboard had really low signal-to-noise, which meant that I was getting really poor signal. And this allowed me to fix it, but the key is that you can use NetSpot or a similar tool, and there are many of them for both Windows. There are many of them for Windows and NetSpot for Mac OS at this point. You choose the one that works. Now there's a particularly frustrating example of what happens when your signal and your signal to noise and your coverage get problematic. So in a vastly reductive way of talking about this, the way that an access point and a client interrelate are that you constantly have an access point on the network saying, hey, here I am, hey, here I am, hey, here I am, and a client will come along and say, hello, can we talk? And that's a request to send. It's basically saying to the access point, can I send data through you? So we good so far? Access point will say, yeah, please, go ahead. And then your client will start to send. Where things get a little squirrely is that when you dig into the documentation for this kind of equipment, you'll find that the Aruba access point has a power rating of 18 dBm. It can send up to 18 dBm of signal out into the air. Well, the iPhone in this case has a power rating for transmission of 15 dBm. So the access point, in effect, I am here, I am here, I am here. And then as I leave my office, walk down the stairs, walk into the parking lot, get in my car, sit down, and decide I'm going to use my phone to look up where that restaurant is that I'm going for dinner, I've still got those beautiful, clear Wi-Fi signal bars across the top of the screen. And I pop open Google Maps and I can't find the thing. It won't load a page or it won't load the data. That's because the Aruba, in this particular case, is effectively shouting at my phone, and my phone can still hear it, but when my phone talks back, it says, hey, can we talk? Hey, can we talk? Hey, can we talk? And the AP can't hear that. And that's one of the reasons why you'll take a phone or you'll take an iPad and you'll walk out into the parking lot and the little visual at the top of the screen says, yeah, I've got Wi-Fi signal, but you get nowhere. Really common problem. So watch that. And again, power levels are really important for this kind of thing, especially since now you have a laptop that transmits at one power level and a phone that transmits at another. Design becomes really interesting. So next up we have co-channel interference. We've seen this before. This is a site that I looked at that had 4 access points, and there are a number of reasons why this site had things configured incorrectly. And the more you know about Wi-Fi, the more horrifying this screenshot looks. But the thing that I really want to key in on right now is that the network hamstring includes 4 access points that are transmitting on channel 9. Now, as discussed previously, access points using the same channel that are able to hear one another are going to generate a large amount of transmission collisions, backoffs, and retransmissions because they're going to be not only are the clients and the access points going to be transmitting in competition, but you're going to scale that up and you're going to have access points and clients that can see multiple access points, adding to that competition. So in this particular example, both of the access points are going to hear the transmissions from one another and they'll end up backing off after collisions. Also, all the devices in the range of each access point. Now the client devices in range of both APs are also going to hear all the transmission from both APs. They're forced, as well as the other clients within range of them. And again, you have a cascading situation. All of a sudden, everybody's backing off, everybody's having to retransmit, and a lot less data is getting through. Similarly, there's a phenomenon called adjacent channel interference, which is similar but a little bit different, and it's a little bit worse. What adjacent channel interference looks like is when you have, and this requires a little bit of explanation, channels also have widths. they take up a certain amount of the frequency spectrum, either 20 megahertz, 40 megahertz, 80 megahertz, or experimentally 160 megahertz. And in this particular screenshot, the person who designed this network elected to take the network APs for hamstring, and instead of broadcast their network in the standard 20 megahertz channel width and the 2.4 gigahertz bandwidth, or the 2.4 frequency band, they decided to double that width and use 40 megahertz channels. The neighbor Cornea did the same thing. And because there's only 11 usable channels in the 2.4 gigahertz band, these two networks overlap with one another, which means they also hear one another. But they don't hear one another in the sense that, hey, can I send? Yeah, you can send. They don't clearly communicate with one another. That is, cornea, the elements of cornea and the elements of hamstring don't clearly communicate with one another. They just collide. And again, resend. And so this is a slightly different type of interference, but since it's not mediated by CSMA-CA, it's a lot less predictable. And in some ways, the behavior is a lot worse. Both of these things lead to contention and congestion. In contention and congestion, clients compete for resources to transmit, and they suffer from reduced performance because of the need to retransmit. And there are a number of tools that you can use to identify this. Wi-Fi Explorer, which is another of Adrian Granados' tools, has the ability to report on access points that are reporting their own utilization. And that's an enterprise feature of some access points. That is, an access point can include in its broadcast announcing its presence that, hey, my utilization is 75%. And you can see that. This is an enterprise feature. A lot of equipment doesn't provide it. I got lucky at Mac DevOps Vancouver last week and was able to capture this on the access points that Simon Fraser University was using. In addition to it not being necessarily the most common feature, it's also not necessarily common for an administrator to turn it on. So a lot of the time it requires the choice of turning it on. But this is great because it lets you see what the access point thinks is the level of utilization on the network and how busy the network is. Another tool called a spectrum analyzer that you attach to a computer or carry around as an appliance can sample and report on the radio spectrum utilization as well. This is a slightly different way of doing this. I've got one attached to my machine here. This is a screenshot from the companion software application, which is MetaGeek's Channelizer Pro, and the display is divided into several sections. At the bottom of the screen, you're going to see a live utilization graph that shows how heavily the radio spectrum in particular channels is being used at that moment, in that instance of sampling. At the top, we have a visual representation of the density of the network's utilization for a given sample period. I typically use 10 seconds because I like to see things change in near real time. In MetaGeek's visualization, red is extremely dense usage. This is a busy, busy network. Blue is a relatively quiet network, and then the range of colors from warmer to cooler indicate varying degrees of use or disuse. And then finally, in the middle third and along the side on the left, there's what's called a waterfall display. A waterfall display is a display of the same density information, but displaying a real-time, second-by-second or minute-by-minute interpretation of it, so you can see how the signal goes up and down as time passes. One of the wonderful things about a spectrum analyzer is that it sees raw radio signal rather than the Wi-Fi signal itself, or rather than only the Wi-Fi signal. And we're going to see the importance of being able to visualize non-Wi-Fi radio signals a little bit later. A third way of visualizing congestion is to use a form of analysis tool that can interpret and display information. You can capture network traffic, search and categorize it, manipulate it, understand transactions. This is a screenshot from a tool called Wireshark. In this example, I used another tool called AirTool to grab around 250,000 frames at the Mac DevOps Vancouver conference last week, just kind of randomly. It was a really busy network. It was a little oversubscribed. It took about 70 seconds to do that. But I went ahead and grabbed 250,000 frames, plugged them into Wireshark, and then pulled up an I/O graph showing the ups and downs, how many packets over time, how many frames over time, and that's the black line. It's probably a little hard to see here because the colors aren't all that differentiated. What I then did was I added a filter searching for wireless retries, and that's a retransmit frame, and graphed that as well, which is the red line. And what you can see here is that if I have a total of about 4,500 to 4,600 frames in this given second, and the number of those that's retransmits is somewhere up in the 1,400 to 1,500 range, then I'm talking about 25% of the traffic on that network at that instance is devices saying, hey, you didn't get this the last time. I'm trying again. Here it is again. Here it is again. Here it is again. And this is the way that this kind of congestion cascades on a network. In a lot of cases, the behavior that ensues, and I think it's the behavior that we've seen here at Mac Admins this week, is for the most part, traffic eventually gets through. You do eventually load Gmail. Slack does eventually load. You do eventually get that download. It might take an hour and a half, but it gets there. And that's a sign of a well put together network in a certain sense. And then for our final common problem, we have radio frequency interference. And you've heard that how many of you have heard that microwaves interfere with Wi-Fi? Hands up. Okay, you've heard that microwaves interfere with Wi-Fi. It's a little more specific than that in the sense that in Wi-Fi we use a 2.4 gigahertz frequency band and a 5 gigahertz frequency band. There are a lot of common consumer devices that also transmit on the 2.4 gigahertz band. It's not just microwave ovens. I'll have a demo of this later. But there are all sorts of security cameras, cordless phones, Bluetooth devices occasionally do this to you, depending on your network and depending on the Bluetooth device. There are all sorts of devices that modify or disrupt a signal, particularly in the 2.4 gigahertz band as it travels, or they add unwanted signal. And this isn't as common in 5 gigahertz because there's just not that many devices out there transmitting in 5 gigahertz that are not Wi-Fi. I suspect that this is probably due to the fact that 5 gigahertz signals are commonly understood not to travel as far and not to penetrate construction materials as well. 5 gigahertz does not pass through concrete, has more trouble passing through drywall, so on and so forth. So a lot of those consumer device makers out there are going, hey, my baby monitor, I need it to get upstairs, in this house. So I don't want it to transmit in 5 gigahertz. But you've heard us say all this. Wi-Fi people, hey, interference, interference, interference. Let me see if I can show you. This is a recording from a session that I did at a friend's house where I went over to just troubleshoot the Wi-Fi. At the bottom, again, you're going to see a live rendering of the utilization in the 2.4 gigahertz frequency band. And at the top, you're going to see a density readout describing the percentage utilization over a 10-second window. In the middle is the second-by-second waterfall display. So let's see if this will play. Oh. There we go. And so it's going to be real normal for a second. And then we're going to pop some popcorn. And it's a little hard to see in this interpretation, but you can see this pattern of high-density transmissions that appears almost immediately. And this will just sit there and sustain until the microwave stops running. As soon as the microwave stops running, that transmission just vanishes, and it goes back to normal in a period of 3 or 4 seconds, and all of a sudden that interference is gone. This is a really important thing to think about with respect to interference, is that some of it's constant, but some of it is transient. You know, that microwave is going to be on for 3 or 4 minutes at a stretch. And if you're microwaving that popcorn while you're starting the movie on your Chromecast or your Roku or whatever, for a few minutes you're going to have no ability to stream potentially, because your 2.4 gigahertz network has just been stomped on. Not as much of an issue in the 5 gigahertz band, but it is something to look out for. And if you're going to go deep into Wi-Fi, then a spectrum analyzer is a really valuable thing to have. I should also mention that a lot of enterprise-grade access points will also provide built-in spectrum analysis so that you can page through your access points and see what they see. And so we talked about those 5 problems. Let me see if I can remember what they were. Coverage issues, co-channel interference, adjacent channel interference, congestion, and RF interference. And so let's talk about a few things that may or may not be strictly Wi-Fi problems. So, start with hardware issues, move on to network configuration, and then talk about implementation issues in a variety of ways, and one that's going to be really important for those of you who are using Apple stuff. So there's all sorts of stuff involved in building a Wi-Fi network that is not actually the Wi-Fi itself. You buy access points, you buy controllers, you buy support agreements, you buy license agreements. Your Wi-Fi controller a lot of the time requires you to buy a license for each access point from the vendor that you're going to control with that controller. And sometimes what you'll find is someone buys a controller, deploys 8 access points and 8 licenses, and then they leave the company and someone else comes along, buys another 2 access points because they think the coverage isn't good enough and they want to add more. They don't need to know, or they don't know that they're supposed to buy licenses for the controller as well. They plug the APs in and then unpredictable things happen. Usually those APs just don't come up. Another issue that you'll run into is that controllers are essentially computers. They have processing power. A lot of the time, they're actually helping move the data along. And if you get out to the edge of what a controller's specs are, you might see the controller itself start to suffer from performance problems. And then finally, we're going to talk in detail in the design section this afternoon about power over Ethernet and power over Ethernet budgeting. But if you have a certain type of power over Ethernet that's the older standard PoE, and you plug a PoE plus access point into it, you may find that that PoE plus access point doesn't power up at all, or you don't get the performance out of it that you expected because the abilities of the access point fall back because it needs more power in order to run at its maximum capability. And then finally, as far as your network infrastructure goes, one of the things that's common enough still is to find that you're plugging in an access point that you've configured to move 450 megabits per second, and that translates in the real world to maybe 200, 225 megabits per second, but you're plugging that into a 100 megabit switch. These are the kinds of things that you think about when you go to design a network. And if you're trying to design a network for capacity and performance, there's a whole process that we're going to talk about later in the afternoon that gets at this. You have to be really careful with it. Network configuration problems can also be a good time. And there are all sorts of these with respect to IP networking. You may not have your IP subnet set up correctly somewhere else. Has nothing to do with your Wi-Fi equipment. You may not have your DNS set up correctly. I've seen all sorts of fun things like, hey, the DNS is supposed to be 10.10.10.21. Somebody set it up at 10.1.10.21 or something like that. Those are common errors. They're going to break people's Wi-Fi connections because they're going to break the ability of applications to move data, but it's not a Wi-Fi problem. You think your users care? No, it's the Wi-Fi. Other things that are interesting about this are VLAN configuration. VLAN configuration is one that bit me recently. So I have a small customer in Seattle that we did a small deployment for. It's an office of 12 or 15 people. We put in 3 access points, a small power over Ethernet switch, and I think it was another 24-port Ethernet switch. And I got it all set up. I built them a guest network. I built them an internal network. I tested it. I walked around. I did a heat map. All of the access points were sitting on top of pieces of furniture because then I was going to have our cabling contractor come out and install them for us, because one of the things I'm not really, if you're a consultant, people don't want you billing them time for going up and down a ladder and bolting things to the drywall or hanging things from the drop ceiling T-rail. It's not a good use of my time. So we get the cabling contractor to run the cables and go ahead and hang the access points. Access points go in, cabling people come out, run the cable, move the stuff up to the ceiling in the locations that I asked, and a day later I get a call. Hey Chris, every time I try to join the network, I'm getting a password error message. Like, the Wi-Fi menu bounces up and down, bounces up and down, bounces up and down. You couldn't join because your password was wrong. So I went back out there, and I found that the cabling contractor had plugged the AP back into a different port on the power over Ethernet switch, and that port wasn't assigned to the guest VLAN. And so, again, it wasn't a Wi-Fi problem. It was a documentation problem on my part. I didn't tell them you have to use ports 1, 2, and 3 on this switch or it's going to break. I didn't think of it. Now I think of it. But you think the users think it wasn't a Wi-Fi problem? No, it's a Wi-Fi problem. Other things that you'll run into are going to include DHCP problems. One of my favorites is doing imaging for a school and just running 200 machines through Deploy Studio. Boot them up, run the imaging process, let Monkey bootstrap the software installs, put them to sleep, throw them in the cart, roll the cart out to the classroom. Had a DHCP scope that had 60 addresses in it with a 4-day lease time. The machines go to sleep, they don't release the DHCP lease, and within a day I'm working with the customer's help desk tech to try to find where in Windows Server I can expire all those leases. Took half an hour, but we got it done, but it's the kind of thing that'll burn you on the Wi-Fi. And you'll see similar issues with DNS. But the thing that I really want to get to is I really want to get to implementation issues that look like Wi-Fi but aren't necessarily Wi-Fi itself. And what I mean by that is it doesn't really have anything to do directly with the physical properties of Wi-Fi and some of the physics and characteristics that we've seen. Who has sticky client problems with their Macs? You all have sticky client problems with their Macs? So who wants to tell me who wants to tell everybody what a sticky client is? Come on.
That's a little heavier than it looks. Basically, when your client moves to a different part of the office, and they're closer to a better AP, but their machine doesn't roam over to that other AP. They're still attached to the old one.
Right. That's exactly it. So, sticky client problem, classic problem for Macintosh, Apple IT in particular. It's something that people complain about a lot. That is, I have a line of APs running through my classrooms. I should be able to walk from one end of my school to the other and have my machine hop from AP to AP. But what actually happens in the real world is that you walk further and further away and the signal gets weaker. And in some cases, the machine never jumps to a stronger AP. And what's interesting about it is that this is more of an implementation problem on the client side, because it's a client's wireless software, wireless drivers, or frameworks that make the final decision to roam from access point to access point. The mechanism for deciding to do this is up to the vendor. Now, Apple published an article describing iOS roaming a couple of years ago, and it contains a lot of really detailed information, but they left us hanging on OS 10 until this spring, when they published another article. And you guys will get these slides. Y'all will get these slides. Apple published a companion article describing this for OS 10, and the rules are as follows. And I want you to go read this article, and then I want you to read it again, and then I want you to read it a third time, because it takes a long time to stick. When a Mac crosses the threshold where its received signal strength indicator drops to -75 or below, it starts looking for a roam candidate. There are a lot of characteristics of what it'll choose to roam to. It tries to go to 5 gigahertz first, assuming a certain level of signal strength. It prefers 802.11ac over 802.11n, which it prefers over 802.11a. And then it also prefers 80 megahertz wide channels over 40 megahertz wide channels over 20 megahertz wide channels. And then it selects and roams to an access point or BSSID to whose RSSI is 12 dBm higher or more than the current BSSID. And I read this article 3 or 4 times at Apple's website, and I felt like something was missing. So extracting all of the other detail, these, I think, are the 2 key points. When a Mac crosses a threshold of RSSI -75, it starts to look for another roam candidate. It then selects a roam candidate whose RSSI is at least 12 dBm higher or more than the current BSSID. Anybody want to take a stab? What's missing? What it doesn't explicitly specify is whether OS 10 will roam if the only BSSID available has an RSSI less than 12 dBm higher than the one that it's leaving. So in order to roam, it looks like it has to meet this threshold, but it's not stated explicitly in the article. So I asked Apple. And Apple said, yes, you're reading that correctly. And this has huge implications for how we design our networks. If I'm walking down the hallway and I get to a point where my current association is that a strength of less than -75, or let's just say -77. I get to -77 and I start looking for a roam candidate. I have to find a roam candidate. What did I say, 77? I said 77. I have to find a roam candidate whose RSSI is -65 or more. And so depending on how I've designed my network, I may never find that. And so the machine will stick. This is something that I just sort of worked through in the last week and had this conversation in the last week. And so I haven't had really an opportunity to test this. This is something that you look for when you go back to your own site and start to play around with this. See if you can confirm that this is true. I'd love to hear about it. Okay, so now we've gotten through all that. Let's take a quick tour through a toolkit and the toolkit that I use to work with and troubleshoot Wi-Fi. There's a lot of terminal tools that are relevant. And again, you'll get the slides. Don't feel like you have to write these down. Some of them are just standard network tools. A couple of my favorites are the ipconfig get packet and then the interface name, which lists out the content of the DHCP packet that interface received from the DHCP server, so you can see what the DHCP server is telling you. That's useful not only in Wi-Fi, but a whole lot of other network contexts. NetTop is a favorite of mine too. NetTop will give you a live view of network transactions that are happening on the machine and the amount of data that's moving back and forth. NetTop is something that I use to see occasionally if an Apple App Store download is continuing because Apple's not giving me any kind of visual representation of progress. And then system scutil-DNS is one that lists out the DNS resolvers that are configured on the machine, and TCP dump will dump packets. But all these details will be in the presenter notes. They're all great things to use. For stumbling and discovery, essentially looking to see what's around me, I highly recommend Wi-Fi Explorer and Wi-Fi Signal as companion applications from Adrian Granados. They'll be worth all $15 or $16 that you spend on them. Fantastic applications. I think that for me, without a doubt, it's the best Mac OS-based stumbler that's available for the Mac. Adrian Granados. I don't know if I'm pronouncing it correctly because I've never met him in person. I've only corresponded. But I think you can go find adriangranados.com. Most of his apps are mostly in the App Store. Other tools that you can use for this, Insider Office from MetaGeek does this as well if you happened to buy a channelizer to do spectrum analysis. NetSpot Pro, the heat mapping tool, will also do this in its discovery mode. It doesn't provide as much granular information as Wi-Fi Explorer does. And then Airport Utility for iOS will also give you some of this information on an iOS device. Tell you things like the strength of networks that an iOS device sees. My understanding is that Apple is fairly controlling of the API access for wireless LAN stuff on iOS, so there aren't a lot of tools. We still have to more or less depend on macOS for this kind of work. And so then if you're going to do mapping, NetSpot Pro is currently the single Mac native application that's available for this. There's a whole lot more whose prices go up and up and up. So NetSpot Pro is an app that I recommend. It's the only one that will actually read data out of your Wi-Fi card because it's the only one that you don't have to run in a VM rendering Windows. Tamagraph Site Survey Pro, Ekahau Site Survey Pro, and NetScout Air Magnet, formerly Fluke, all make great applications that do the mapping and then a whole lot more. They get into planning, and we'll see some of that in the planning section. The price escalates very rapidly. I think the last time I looked at Tamagraph, it was about $1,300, and a complete set of Ekahau Site Survey Pro runs you somewhere between $5,000 and $6,000. So that's really if you're going to get really, really serious about this. I've been fortunate enough to be able to borrow a copy, but I don't own a copy of my own. The MetaGeek Channelizer Pro, the little antenna that I have hanging off the back of my laptop, rather the MetaGeek Wi-Spy works with MetaGeek Channelizer Pro, which is and that's the combination that I have on my laptop, allows me to grab raw radio signal like we saw with the microwave oven. If you want to get your feet wet, you could also buy the less expensive MetaGeek Insider Office, but it doesn't provide as much information. Specifically, it doesn't really provide time-based controls and waterfall displays, but it's a handy tool to have. I own it. And then recently, I have that misspelled on the slide, a company called ASYMMETRY, and I do apologize for that. OSCIUM has been developing what they call a Wi-Pri 5 gigahertz, which is a spectrum analyzer similar to this that hangs off of the lightning port of an iPad. And that's still in very early development. I've played with one. I haven't really gotten comfortable with it yet, but look for that to come down the road. And hopefully it's a sign that there will be more tools for iOS soon. And then as far as packet capture and analysis goes, Adrian Granados wrote a third tool which is free, and that's called AirTool. AirTool sits in your menu bar and allows you to pick a channel and kick off a wireless capture. Just capture the data going back and forth over the air. You then feed that data to a tool like Wireshark to do analysis, or to something more Wi-Fi specific like MetaGeek IPA, which actually allows you to do packet analysis as relates to wireless features and wireless capabilities. One of the things that MetaGeek IPA is really handy for is analyzing a more sophisticated concept called airtime utilization. That is there a client that is stomping all over all the rest of the client's ability to transmit because it's eating too much of the time that's available to transmit with? We're going to talk about airtime when we talk about design this afternoon, and it breaks my brain, it'll probably break yours. It's a complicated, annoying concept, but we're going to have to deal with it. And then Cloud Shark lets you do things like Cloud Shark is a service online that allows you to upload your capture files and analyze them through a subscription service. So you can share them with others, see what other people think. And then for traffic analysis itself, again, Wireshark and IPA. And then for logging, Apple has a wireless diagnostics tool built into Mac OS that will capture all sorts of things for you. And it's the kind of thing that you want to run when you're talking to Apple, and Apple says, hey, we'd like to capture logs of your sessions from a machine. Go find Apple Wireless Diagnostics. And not only does it capture Wi-Fi logging, it will capture DNS logging, capture system logging, capture Bluetooth logging, all of the things that can tie together to affect your Wi-Fi connection. As always, Apple Console is useful. And then I want to call out the hidden Apple Airport command, and that's documented in the presenter notes. There is a long path in, I think it's System Library Frameworks, somewhere in Apple's core WLAN framework, there's an airport command line tool that allows you to do things like scan for networks the way that Wi-Fi Explorer does, change logging settings on your Wi-Fi interface, and do things like dump logs and sniff traffic. Questions from y'all? Comments? Abuse?
Throw a comment out there, like in that troubleshooting aspect, when you were mentioning DNS and DHCP and all that fun. If you do anything with like your guest networking and you have different VLANs and they're isolated, you have to sometimes also worry about firewall rules and then natting that information back and forth.
Sorry, what? Oh, sorry. Randy.
All right,
I was so good about it earlier.
I'll do this one again then. If you're separating any of your traffic with guest networks and you want to isolate that information, you do have to watch out for firewall rules between those guest and production networks as well as NAT translation. So if you do any of that, just kind of keep that in mind, that sometimes that can come and bite you as well.
Anybody else?
Right.
Thank you.
Cool. Testing. Okay. So one thing about the 5 gig that you said doesn't transverse through a lot of materials, you can actually leverage that to help you, which is what we did in our classrooms. We switched to 5 gig only, so the signal theoretically doesn't escape the classroom. So when the kids move from one classroom to another, the device is forced to roam.
That's exactly right. And when we talk about design a little bit later, we'll see that that's an element of thinking about your design, that you can actually use some of the limitations in order to do better. Anybody else? Because I do have some demos. And I want to see how many of those I can get through. I've got to see if I can configure my screen to show these off. I want to try to just show you Wi-Fi Explorer and Wi-Fi Signal just real briefly. We'll review a heat map that I did with NetSpot. I'll do a live demo of radio frequency interference with my channelizer and with the Infant Optics baby monitor that I brought with me. And then I want to see if we can burn down the Wi-Fi, if anybody wants to give that a try. So we'll give that a shot. So let's see how many of these I can get through. Turn mirroring on. Are we good? All right. So let's bring up Wi-Fi Explorer. This is what Wi-Fi Explorer looks like. You've seen this in some screenshots. And this is viewing all of the Wi-Fi in the vicinity of my machine. And you can see on the left-hand side the names of all the networks and also different categorizations. So you can see 2.4 gigahertz networks versus 5 gigahertz. So if I just want to see what's available in 5, I select that. If I just want to look at the AT&T Wi-Fi network and have it show me the elements that are included in the AT Wi-Fi network, I can do that. I can view signal strength of networks over time. I can grab a particular network and review some of its details, including the signal strengths and noise levels that my machine has detected, a little bit more technical information like whether the administrator has set a minimum rate, that is, my machine must be able to achieve this transmission rate or it gets booted off the network, which is something that's going to be really handy. And then digging into advanced details, I can actually look at the contents of the beacon frames that the network uses to advertise itself. Looking at Wi-Fi signal at the top, this is a nice application that provides a much cleaner view of network capabilities than Apple's Wi-Fi menu item. You can see signal, you can see noise. It gives you an evaluation of the quality. My signal level is apparently excellent right now. And it shows me, it actually calculates the signal to noise for me. And that's something that Apple doesn't do for me. It's a nice little detail to have. Oh, let's see. One final thing that is really kind of neat and really helpful if you're in the same facility all the time is the ability to annotate networks. So I can annotate the network, apply a note to it. I can either give it a label, and then you'll see here that the annotation shows up in Wi-Fi signal saying that, hey, you labeled this as Chris's presentation network, so this is what you're attached to. So if you have a facility where you're dealing with the same 8 or 12 APs, you can use Wi-Fi Explorer to annotate your APs and more easily see what you're attached to as you walk around. It's kind of a handy little thing. So then I'm going to dive into NetSpot for just a minute, and I'll go back to my office survey, and I will find it is a little bit complicated to do. I will find my 5 gigahertz access points and fill in a visualization. I think that's right. And this is the visual, this is the live version of what I was showing you earlier. I had 2 access points located near the back of the office, did a walkthrough, and my 5 gigahertz connection ended up looking like this. And clicking on each of the individual points in the survey, I can display what was detected at that particular point. And a lot of the heat mapper applications will do this for you. It's not confined to NetSpot. If you have a VM, you're going to get fuller features probably out of some of the other tools, but NetSpot is also a great way to start. Other things that NetSpot can do is give you evaluations of various forms of trouble. You tell it what your values are, that is, what you prefer your signal to be, and it will tell you places where you don't have sufficient signal to noise ratio in order to meet that expectation. So NetSpot's pretty handy that way. It can also do before and afters. So if I do the same visualization of signal to noise ratio, after I decided to move one of my access points to the ceiling, we get lots more warm, lots more evenly distributed. Pretty handy. And so then, I'm going to try one last thing, and I got to disconnect my presenter remote and connect an external Wi-Fi card to my available USB. I'll get into Channelizer. And because VMs are a little squirrely, I'll hope that I get to unplug and plug in my spectrum analyzer again in order to get it recognized. And then I'll wait because it just seems to take a while. And here's a live view of the 2.4 gigahertz spectrum. So density at the top, there's a pretty busy AP, looks like on channel 6. There's a lot of red there. There's a lot of utilization down there at the bottom. And I have an Infant Optics baby monitor because y'all need watching. So I'm going to turn that on, and y'all just keep an eye on the screen, and let's see what happens. And so all I've done at this point is turn the camera on to watch the baby. I haven't turned on the receiver yet. Let's do that. Gets a little bit worse, doesn't it? So, I learned about this from the same friend whose microwave you saw, because what he actually called me over for was, ever since we had the twins, we haven't been able to watch movies. And twins, they can't watch movies anyway because twins, but then this became a problem. Like, the kids' room was upstairs, they had this receiver downstairs, the TV was right next to the wireless access point. I'm going to go ahead and turn this back off because Randy doesn't actually need watching. And then here's what I'd like you to do. Let's take a look at the 5 gigahertz band instead and see how busy we are in the 5 gigahertz band. And then what I would like to do is I would like you to go to this link at Apple's support site and go ahead on your Macs, start downloading the El Capitan 10.11.5 combo updater. As many of you as I can get on your current conference Wi-Fi connection. And let's just see what happens. How many people am I going to get to try to do that? Okay, so I'm going to leave that URL up for a minute because it's longer than I would like it to be. And just tell me once you've got it plugged in, and then I'm going to switch back to the spectrum analyzer. All right, seems like that might be enough time. Oh, sad preview. How about now? Now? So it's going to take a long time for these downloads to complete. And the thing that I want you to pay particular attention to, first of all, the density. We're transmitting, retransmitting, transmitting, retransmitting. We're going to overload these APs, and the utilization has spiked to about 100%. And if you read the documentation with respect to what you should be doing for design, the luminaries in this part of the business say where you really want to be is 40 to 50% and no more than that. So anybody else who was trying to do anything in Wi-Fi probably for the next 2 rooms around just got real sad. So maybe that means that there's fewer people slacking and more people paying attention to their respective presentations. I hope that's the case. But anyway, thank you.